Ohm's Law for Electricians by Electrician.
What's up, and welcome to Electrical Solutions YouTube channel. Today we're going to be talking about Ohm's Law and how it pertains to the electrician. It's taught by an electrician, which is myself. I am a certified journeyman in the state of California. I just passed my C10 license out here as well, so I'll be contracting my own work very, very soon. And I'm also a licensed master electrician in Nevada. So I'm just trying to give you a rundown of what I think is important pertaining to the field. So it's important to understand in calculations and express terms that there is a difference. When you calculate things, you'll see the Ohm's Law wheel, and it'll have P, typically E, I, R, not usually Z, it'll normally be R, and sometimes the E will be a V, but those have specific meanings. P is for power, the E is for electromagnetic force, or also known as voltage, I is for current, the R or the omega is going to be resistance, the HZ is hertz, the Z or the omega is impedance when you're talking about an AC circuit. The resistance is mainly for anything without capacitance or inductance, typically DC, where the impedance will be AC. And when you're writing out your answers or calculations, once they're done, it will be in the express terms. The express term of power is watts. The express term of electromagnetic force is volts. The express term of current is amps. For resistance, it's ohms. Hertz, it's hertz as well. Impedance, it's also ohms. As you can see, I have the corresponding letter or abbreviation for whatever it is next to it. For watts, it would be W, volts would be just the V, amps is the A, ohms is typically written out, or the omega. Hertz is going to be HC, ohms is going to be ohms. So a hertz right here, this is the typical sine wave. Plus and minus. When the generator is spinning, it's creating this due to the magnetism. This section here is 1 hertz. Whether it's in the United States, typically 50 or 60 hertz, mainly 60. That will be 60 of these per second. So that is basically 1 revolution of the generator in 1/60th of a second, if it's 60 hertz. So that is 1 cycle, 1/60th of a second. So for 1 minute, if you were to time 60 seconds, which is how many seconds are in a minute, times how many revolutions per minute, which would be 60, it would be 3,600. That's important for synchronous motors, but just an idea of how fast that generator is actually spinning to get to that. So for impedance is AC, as I said earlier. Sorry for repeating myself, I do that a lot sometimes. But that's going to be this formula here to get it, which is resistance squared plus the effect of inductance minus the effect of capacitance. It's actually inductive reactance and capacitive reactance, but we're not going to talk about that. Squared, added to resistance squared, and then the square root of that gives you impedance. That's important because things change when you use AC compared to DC, and it has an extreme effect on your power quality as well as how much power that you have that is actually being used. So nowadays you usually have a multimeter that can do most of this stuff, if not all of it, but they're not always accurate. the further along we get, the better they get. But if I was to try and find exact power, I would use a power quality meter. Power quality meter is the one you put clamp-on meters on each one, and then you also measure voltage, and it gives you an exact reading on what's happening in your power, from your power factor, from your capacitive reactance, your inductive reactance, all of that good information, reads volts, amps. You can also get that typically with a multimeter, like I said before, once again repeating myself. For volts, I'll just use a multimeter. There is voltmeters that will work for that as well, but good multimeter will do that. Amps, I usually do it with a clamp-on meter, which is, in my case, I have a Klein one that does that. Ohms, depending on what kind of ohms you're measuring, if you're measuring insulation ohms compared to actual wire, how much ohms is in between a set of wires or whatnot. For the resistance, or for both of those, you can use the megameter. It will have both of the readings. That's probably going to be your best bet. For insulation only, you can only use the megameter. I'm not aware of a multimeter that does one. There probably could be one, and if not, there probably will be one soon. But I guess it would be a mega as well. But you can also use a multimeter for just regular ohms. For hertz, typically you'd use an oscilloscope or a power quality meter, because then you can actually see on the screen the true sine wave and what's going on there. For impedance as well, you want a power quality meter, because it's going to measure actual power, how much you're using, compared to apparent power, and that's due to your power factor, which is basically the difference between resistance and impedance, but in a roundabout way due to inductive reactance and inductive capacitance. So the next thing that we're going to be discussing is going to be the AC sine wave, and as you can see here, you have a plus and a minus. That's going to be your plus side and your minus side for when the sine is going like this. That line is going to be 0 volts, and you see I have it divided into 4 sections, correlating with these down here. Now this top piece is going to be your peak. In here is going to be your medium, which is going to be between the peak and 0, and you're going to have a negative medium as well. So usable power is not the peak or the median. It's going to be determined by a thing called RMS, root mean square. The way we get that is we take the peak, divide it by 0.71, and that will get our root mean square, or our actual usable voltage. Now, the way power is produced is you'll have a conductor inside of here. This will be a set of magnets that the conductor will actually spin inside, and it will be creating voltage on that conductor, right? So as it's spinning north-south, imagine it's spinning clockwise, okay? As it's spinning clockwise and it gets to this next state here, so it would be this side, it turns halfway, or it turns a quarter turn, that then gets us to right here. As it then gets to the next quarter turn, it comes on the downside here. And then once it spins that other way, it goes to peak voltage here, and then from peak voltage it goes here as well. This is important because it's not only the way that a generator works, but it's the way that a motor works, but the rotator and the stator, or not the rotator, the rotor and the stator are just switched. Now regarding series circuits are always going to be the same. What a series circuit is, it comes from one side, comes into that, comes out of it, and then continues on. So if you were to add more loads in it, you would draw them in series like this, coming in one side, out of that to the positive side on the next, to the positive side on the next one, and the last one going to the negative side. We're not going to do a problem like that. We're just going to do one simple series circuit. So for series circuit, PT, which is power total, is going to be, it's going to be total P1 plus P2 equals PT. Voltage, the voltage drop across one and the voltage drop across the next one is going to equal the total voltage drop. Now, no matter what, your current is going to stay the same if you have more than one load. Always. Your resistance is going to be the total resistance equals first resistance plus the second resistance. Now, there is a Ohm's law wheel that is very good in explaining. Really, you only need 2 parts of Ohm's law to determine the rest of the problem. So right now we're given volts and amps, so we need to find out how much ohms we have and how much wattage we have. So let's say I want to find out watts, but I have volts and amps. So I cover that and I take I and I times it by E. So 10 times 2 is going to be what? 20. So we're going to have 20 watts. Now, if I have E and I want to find out R, I cover R, which is then E over I, or volts over amps, right? So 10 divided by 2 equals 5. So I have 5 ohms. Let's make sure that all checks out, right? So if P is equal to 20, E is equal to 10 volts, I is equal to 2 amps, or R is equal to 5 ohms, let's make sure it all checks out. To get P, let's do I times E, right? So 10 times 2 is 20. Checks out. We're good. So for I, we cover I and we got P over E. So we have 20 over, so it would be I equals 20 over 2, or 10, excuse me, would be 2. We have 2 amps. Checks out. Now, let's say we want to do volts. We cover E, we got P over I. 20 over 2 equals 10. 10 volts. Checks out. Now, to get R, in this situation, we have E over I. 10 volts over 2 amps equals 5 ohms. 5 ohms. This all checks out. Now, it changes a little bit when you add one more to it, but not too much more. You just follow these guidelines. As long as the total checks out, you're good to go. Parallel circuits differ from series circuit in the fact that they have more than one path. Series circuit is only one path. You can add as many loads as you want, but it can only take one path to go through those loads. The way we wire receptacles is here, right? Because if we come off our hot wire, we come to it, we'll tie it together and pigtail it off one and take it to another receptacle, where we then pigtail it again using the screws to another one. That is essentially the same thing here. If we were to wire receptacles in series, we would wire them like this. One screw, hot screw, right? Negative screw. We would take it from the negative screw, take it to a hot screw here, and so on and so forth. The problem with this is if there's not a load in here, this receptacle is not going to work. And then if we have 120 volts, but you use all 120 volts, or you have two different loads with the same resistance, you're going to split that voltage in half. So you would get 60 volts here and 60 volts here. The good thing about parallel is we will have the same voltage across it no matter what, and that's why we wire receptacles in parallel. Now, for them, the total watts is equal to the watts of 1 plus the watts of 2, the power. The voltage is equivalent all the way across. So we know that it's going to be 20 volts here as well and 20 volts here. The amount of current changes from series and goes total current is equal to the current of 1 plus the current of 2. Now the thing that changes and confuses a lot of people, especially myself when I was first learning, is this formula. So the total resistance is going to be lower than your smallest amount of ohms. How does that work? Now it works based off this formula here, right? So to find our total resistance, we have 1 over, we take 5, 1 over 5 is going to be 0.2. So we would then take 0.2, and because they're the same, it's the same thing, 0.2 is equal to 0.4. So we have 1 quarter. 1 quarter is going to be, or 1, not 1 quarter, excuse me, 1 divided by 0.4 is going to be 2.5, which is lower than 5. Now, we know that 20 volts, or excuse me, we know that voltage is the same across. So if it's 20 volts here, it's going to be 20 volts at the total. Now, we have voltage and resistance. So if we want resistance, we cover that and we get E divided by I equals resistance, right? So we're not solving for I there, or we're not solving for R there, we're solving for I. So we cover it, it gives us E over R equals I, which is 20 over 5 equals I. So we know that's the same on both of these. So you get, what did I do there? 4, sorry. We got 4 amps, right? So the total is 1 plus 2. So 4 plus 4 equals 8 amps. Now to figure out our wattage, and I didn't explain this earlier, to figure out the totals you need to break down each problem. So this is a problem, this is a problem. If we were to add more in, that becomes its own problem, and then you combine it into the problem for the totals. So if you were to add totals, it would be plus P3, so on and so forth with the formulas. Now we now need to find total watts, right? Which if we want watts, it's amps times volts. So we have 20 volts times 4 amps, which is going to give us 80. So it's 80 here. It's also going to be 80 here. And 80 plus 80 is 160. And it checks out again because 20 times 8 is 160. If we were to divide 20 by 2.5 ohms, it would give us 8. Everything is good to go. Now, typically you're only going to see things wired in parallel. There is series circuits, which are typically going to be motors. Now, there is times when it can change. So there is times that it can change. Let's say this is your transformer. This is phase A, this is phase B, this is your neutral, and this is a single phase 120, 240 volt transformer, right? Now, let's say your light is turned off. This circuit is open, and you have it coming off from A phase, coming down to one receptacle, and you only have one thing plugged in your house. That is actually a series circuit. Or a series circuit can also be a dedicated circuit. Now, as a whole, the system is series, as long as it's just this one. As soon as you turn this light on and you have this on, it then becomes parallel because it's taking two paths. Now, your dedicated outlets or dedicated appliances are going to be wired in series because they're going from point A, serving a load, and back. But that doesn't mean the whole system is series, because if you have any other loads off that phase, it then becomes a parallel path, meaning more than one path is available, and it changes. So instead of it just being a 120 volt drop across this, you would then have 120 volts here and here, because it is now a parallel circuit. Now that will change as loads change in your house. Generally, you will never see just a series circuit or a whole system with the transformer, the panel, and everything series. Very rare, unless it's some type of dedicated equipment for that. Normally it's all going to be parallel as a system. Now you can have the circuit series and another circuit series, and it will make a parallel system. Kind of confusing, but all the difference is a series is one path from A to B, one load, right? That's it. A parallel is more than one path, more than one load. Now you can have a system wired in parallel, but if only one of those loads is working, it then has become a series circuit because you only have one load. Kind of confusing, but planting a seed, eventually it will make sense. Impedance, which is Z, R is resistance, is ohms plus the effect of capacitance minus the effect of inductance, right? And what's going to happen there is you're going to have a sine wave for voltage and a sine wave for amperage, right? If they shift because of capacitance or inductance one way or another, and they're not, let's say the current sign is slightly behind it or it lags it, it's going to adjust your power factor, okay? And that power factor adjustment is going to be in a ratio expressed by a decimal. So let's say it's 90 and you have 100 VA, right? Power factor's there. You're then going to only be using 90. It's only going to be 90 watts. You're generally going to have more inductance than you are going to have capacitance, and that's because you have more inductant loads. When you wire a house, you will make loops. Any loop will cause inductance to happen. You have transformers which use inductance by nature, but that's exactly what it is. It's an inductor. So when you see watts, you got to remember it's VA times PF. So this is actually what's known as apparent power, and this is actual power for watts for AC. DC, your actual power is going to be expressed in VA because you don't have as much effect. You do have an inductance and capacitance effect, but it's not as great as it is in AC because of the nature of the sine wave going up and down and everything that's going on there. So it's important to remember when you see Z, it is including capacitance and inductance, which creates your power factor, and a low power factor is a low quality of power, as well as harmonics and some other things. But when you have a low power factor, you will lose more power, and there can be, I don't want to say fines, but penalties from the utility for that. They promise to deliver you at a certain percentage, and your meter will actually read power factor as well, because it's able to tell how much VA it's sending, and it's able to tell how much wattage you use. So if it's not within their guidelines of what they're providing and what they say they'll cover, you will actually pay more for that power. All right, well, thanks for watching the video. I hope that was informative. And if you have any questions, you can shoot me an email at the email on the screen, and I'll be more than happy to answer. Thank you guys, and have a good night.